Okay, Assalamualaikum and good morning everyone. It's me again, Madam Fatin, for Physics Lecture EP025. Okay, so for today we are going to look at Chapter 7, which is Physical Optics. Okay, so before we start here, I've got a motivational quote to share with all of you. If you are not willing to learn, no one can help you. If you are determined to learn, no one can stop you. So this really means that your study is your own responsibility. Okay, if you are watching this lecture right now, then it is good for you. Congratulations, right? Okay, so what are we going to learn in physical optics? Okay, previously in chapter 6, we have looked at geometrical optics. Okay, so what are the differences between physical optics and geometrical optics? Okay, in terms of geometrical optics, it is another branch of optics that has to do with the principle that govern the image forming properties. Okay, meaning that we are talking about the image formed by lenses, mirrors, and any devices that make use of light. Okay, so in chapter 6, we are treating light as ray, sinaran. Okay, but for physical optics, we are going to look at light in terms of the wave phenomena. Okay, so we are going to discuss about interference, diffraction, and polarization of light. So what is interference? Interference, if you translate it to Malay, adalah gangguan. Okay, so this one we have seen in semester 1 where we can get the constructive interference and destructive interference. Okay, so the same things we will discuss here. And then diffraction is pembelauan, where it occurs when a wave passing around obstacles or passing through openings. Okay, then diffraction of light will occur. The next is polarization of light. Okay, polarization, the definition is pembahagian. Okay, so this is the example of polarization of light, where we can see a colorful formation, for example, on the surface of the oil spillage. Okay, awak tengok dekat minyak kalau ada atas tanah tu kadang-kadang ada macam rainbow color. So that is polarization of light. Okay, so remember in physical optics, we are treating light as wave rather than as rays. Okay, gelombang versus sinaran. Okay, so this is the overview of what you are going to learn in chapter 7. So for today, we are going to look at Huygens principle and then interference system. So the rest will be covered in the next lecture. Okay, there are 6 subtopics for chapter 7. Okay, so we are covering the first 2, Huygens principle and constructive and destructive interference. So the 7.2 will be quite easy for you because you have learned this in semester 1, right? Okay, so let's start off with Huygens principle. The learning outcomes is students should be able to state the Huygens principle in the context of spherical and plane wave fronts. Okay, and then next, sketch and explain the wavefront of light after passing through a single slit or obstacles. Okay. So a bit of introduction to waves. Okay, so we are going to look at some of the terms that you will often see in chapter 7. Okay, the first term is ray. Ray is defined as a line represents the direction of travel of a wave. Okay, so this is the ray, showing that the wavefront propagating to the right. Okay, and it is right angle to the wavefront as shown in the figure. So this is the wavefront, the side of the wavefront. So this is the ray, so they are always perpendicular. And the distance between the 2 consecutive wavefronts is called the wavelength, right? The next term is wavefront. Okay, so wavefront is a line or surface in the path of a wave motion on which the disturbance at every point have the same phase. Okay, so consider we have a wave over here on the right hand side. Okay, and if we labeled all the crests A, B, C, D, E, F, and the line joining all the points of the adjacent wave is called the wavefront. Okay, if we translate to Malay, if I'm not mistaken, it's muka gelombang. Okay, and the wavefront always perpendicular to the directions of propagation. Okay, so you can see the 90 degree here, right? And the same, this is the wavelength, the distance between two consecutive wavefront. So let's take a look at different types of wavefronts. The first one is circular wavefronts, where it is produced by a point source that is able to generate two-dimensional waves. Okay, so this is the point source. This is the circular wavefront. This is the directions of the ray, which means that the wave propagating outwards from the source. And next, this is the wavelength. Right, so then we move on to spherical wavefront, produced by a point source that is able to generate three-dimensional wave. Okay, so just now is 2D, this one is 3D. Okay, so the same thing, point source, wavelength, wavefront, and the ray. Okay, and the last one is plane wavefronts. Okay, plane wavefronts is also produced by a point source that is generating three-dimensional wave at larger distance from the source. So this one is at the larger distance from the source. We can see the wavefront is a plane. Okay, this is the side view of the wavefront. Okay, we can see a number of lines perpendicular to the rays. Right, so we are going to discuss about Huygens principle. Okay, so who is Huygens actually? Okay, the name of Huygens is Christian Huygens. He is a scientist, a physicist, mathematician, and who is really well known for his light wave theory. Okay, so what did Huygens principle says? Okay, every point on a wavefront, okay, can be considered as the source of secondary wavelets. Okay, so this is the wavefront, the initial wavefront. Okay, and every point on the wavefront is a source. So imagine that the dotted circle over here is 1, 2, 3, 4, and so on, representing the point sources. So for every point source, they are able to generate the secondary wavelets. Okay, so this is the secondary wavelet for point A. Let's say this is point 2. This is the secondary wavelet. Okay, so wavelet is actually a small waves, right? And then the secondary wavelets spread out in forward direction at the speed of wave. So this is the series of wavelet. Okay, and then what happened to the wavelets? The new wavefront is the envelope of all the secondary wavelets. If you draw the tangent for each wavelet, you will get a new wavefront. So that is what Huygens principle about, right? Okay, so let's take a look at some animation over here. So imagine that this is the old wavefront or the initial wavefront. Okay, so Huygens says that every point on the wavefront is the source for secondary wavelet. Okay, so here I have 11 points, alright? And then each point will have their own wavelet. Okay, so this is a series of wavelet, and if we draw the tangent for all the wavelet, we'll get a new wavefront. Okay, so hopefully you can understand that. Okay, so now that we already know what is Huygens principle, you should be able to explain the constructions of the new wavefront. The first one is for the plane wave. Okay, so this is the plane wavefront. Okay, if the wave speed is v, hence in time t, the distance travelled by the wavelet is s equals to vt. Okay, so this one is from the formula velocity. Velocity is equals to displacement over time. So to get the displacement, the formula is v times t. Okay, so you can see here, this is the s, the displacement or the distance travelled by the wavefront. Okay, then from Huygens principle, points P1, P2, P3, and P4 on the wavefront are the sources of secondary wavelets. Okay, so where is the wavelet? This one. Okay, how do we draw the wavelet? Is by drawing the curves of radius s for each point, right? And then when we draw a straight line, which is the tangent to the curves of point Q1, Q2, Q3 and Q4, we get a new wavefront. Okay, so hopefully you can see the flow. Okay, now the construction of new wavefront for a circular wave. The explanation will be the same as of the plane wavefront. Okay, but the difference is that the new wavefront is a curve. Okay, you can see if we draw the tangent for the wavelets, we get a curve, okay, instead of a plane, right? So this is for circular wave. Okay, that is quite easy. Then we move on to the next, which is by using Huygens principle, we can explain diffraction of wave. Okay, diffraction is pembelauan. Diffraction of light at a single slit. So slit is a small opening, or we can say celahan lah. Okay, celah-celah. Right, so from here in the diagram we can see this is a plane wavefront moving through a slit. So this is an opening. Okay, so what does Huygens says at first? Each point in the figure acts as a secondary source of wavelet. So this is the wavelet. Okay, and then the tangent to the wavelet from points 2, 3 and 4 is a plane wavefront. So you can see directly in front of number 1 till number 5 is a straight line. So this is plane wavefront. Okay, but the edges point 1 and 5 are the last points that produce wavelet. So you can see number 1 and number 5 produce the last wavelets. Okay, so Huygens also suggests that in conforming to the curve shape, meaning that in obeying the standard behavior of the curve shape, so the new wavefront bends or diffracts around the edges. Okay, so hopefully you can see the difference between plane wavefront and then circular wavefront. But for diffraction through a single slit, there will be curve or bend at the edges. Okay, so this all is using the Huygens principle. Okay, so we go to lesson check. Okay, you can drop your answer in the chat box. Right, so one evidence that shows light as a wave phenomenon is that light can undergo diffraction and interference. Okay, so I have mentioned the difference between geometrical optics and physical optics. Right, so lesson check 2. Okay, which of the following method will result in a new wavefront? Okay, so joining all the tangents to the wavelets. Right. Next. Right, so which of the following statements shows the relationship between the wavefront and the directions of the wave? So find the keyword over here is perpendicular. Right, so the answer is B. So do we have another question? No, okay. So we move on to 7.2, constructive and destructive interference. Okay, so the learning outcomes is you should be able to define coherent. I think this is the same learning outcomes from semester 1. Okay, so you need to know what is the definitions of coherent. Then state the conditions for interference of light. So what are the conditions for the interference of light to occur? Next, state the conditions of constructive and destructive interference. Okay, so we are going to discuss the conditions in terms of the path difference and the phase difference for constructive and destructive interference. Right? Okay, so what is light wave? Light wave is an electromagnetic waves, which means it consists of varying electric field and varying magnetic field, which are perpendicular to each other. So you can refer to the diagram over here. So this is the electric field with the red color. and the magnetic field is the blue color, right? So one thing about light wave is that it will not be deflected by the electric field or the magnetic field. So light wave can travel in straight line, okay, and it does not require any medium. Unlike mechanical wave, such as water wave, so the wave needs mediums, which is water, to propagate, but for light wave it does not require any medium. Okay, so what is interference of light? Okay, so I think that most of you already know what is interference of light. It is the effect of interference between two or more waves which overlaps or superpose. Okay, so this is the water wave. Okay, the light wave behave exactly like the water wave, but it's just that we cannot see the ripples, we cannot see the constructive and destructive interference here. Okay, for light, the interference occurred when two light waves meet at a point. Okay, so the region over here we cannot see it, but if we put a screen at a distance from the source, so this is source 1, source 2. Okay, so a screen over here, you can see the bright or the dark region. Okay, so this is the bright, this is the dark, which the two regions produced by obeying the principle of superposition. Okay, so a bit of recap from semester 1. Principle of superposition is the resultant displacement at any point is the vector sum of the displacement due to the two light waves, and we will get constructive and destructive interference. Okay, so still remember that wave consists of crest. Crest is the highest point and trough is the lowest point. So when the crest meeting with the crest, we will get constructive interference. Okay, the same when the trough meeting with the trough, we get constructive interference. Okay, for destructive interference, when the opposite point meets each other, so this one is the crest meeting with the trough, so we get destructive interference. Okay, see my slide? Yeah. Okay, next we move on to conditions for permanent interference. Okay, so okay, what are the conditions to get a permanent or a clear interference? Okay, the first one is the two sources of light are coherent, which means that they have the same wavelength and frequency. Okay, so this one means the same because the formula is F equals to 1 over lambda. Okay, so you can say same wavelength or same frequency. Then constant phase difference between them. Okay, so this one, let's say if at the starting point the 2 point sources start with a difference of lambda over 2, for example, and until the end they will maintain lambda over 2. But this one is in terms of phase difference, so pi over 2, for example. Okay, so they maintain the same difference from the starting point until the meeting point, right? And then the second is the light wave that are interfering must have the same or approximately of the same amplitude. Okay, so this one is in order to obtain total cancellation or obtain a good contrast at maximum. Okay, meaning that if the crest meeting with the trough, positive 2 plus negative 2, we get a clean 0. Okay, so that is a total cancellation. Okay, number 3, the distance between the coherent sources should be as small as possible. Okay, so for example, the Young's double slit experiment, the two sources should be kept as close as possible, smaller than the light wave that we use in the experiment. Okay. Okay, next. So just now is just like general conditions for interference to occur. So for this slide, we are going to look at in terms of the condition for constructive and destructive interference specifically. Okay, and we are discussing in terms of the path difference. Okay, so what is path difference? It is the distance difference in distance from each source to a particular point. So let's say here we have two sources, S1 and S2, and a screen. Okay, the two waves, they meet at point P. Okay, so the distance between S1 to P is the x1. the distance between S2 and P is x2. Sorry. So the path difference is delta L. Okay, so how do you calculate the distance between the two paths? So we just subtract the two, right? Okay, so x2 minus x1. Okay, so here is how we are going to determine the path difference for constructive and destructive. Okay, so first we are going to look at in terms of path difference for constructive interference when the two coherent sources in phase. So how do we know that the two coherent sources are in phase? Okay, so this one we need to look at the starting point of the two sources. S1 starts with a positive cycle, the same goes to S2, so meaning they are in phase. Okay, but this one, we cannot use this one to determine the type of the interference. The type of the interference depends on how they meet at a point. So at point P here we can see that they are meeting at the same point. Okay, so starting from that point, they will propagate as one wave. So meaning they have been constructively developed. Okay, so this is constructive interference. Okay, so in terms of the path difference, okay, I want to calculate the path difference in terms of the wavelength. Okay, so focus on the source one. So how many wavelengths can you see? 1, 2, 3, 4, 5, 5.5. So for S2, 1, 2, 3, 4, 5.5 also. So what is the difference between them? Okay, 5.5 minus 5.5, so 0. Okay, so the conditions for constructive interference to happen for two coherent sources in phase is when they have a difference of lambda. So in the example just now, it's 0 lambda. Okay, so the number m, so the m is the order. We can change it to positive 1 or plus minus 1, plus minus 2. Okay, so when they have a difference of lambda, it will produce bright fringe. A difference of 2 lambda, also producing bright fringe. Okay, so in order to get a bright region, they need to have a difference of m lambda. Okay, so that is constructive interference for in phase. Okay, now we are going to look at the destructive interference for in phase as well. So how do we determine the in phase again? Okay, so we can see that the source S1 starts with a positive cycle, S2 also with a positive cycle. So they are in phase. Okay, so to determine the types of interference, we look at how they meet at a point. So this one, they meet the opposite cycles meeting each other. So what will happen? They will cancel out and become destructive interference. Okay, so now let's count the wavelengths again. So S1, 1, 2, 3, 4, 5, 5.5. Okay, for S2, 1 wavelength, 2 wavelength, 3, 4, 5, and 6. So what is the difference? 6 lambda minus 5.5 lambda. So we get a difference of half lambda. So that is the condition for destructive interference for in phase. Okay, you can see here we have a difference of half lambda. And if we have a difference of 1.5, also we will get dark fringe. 2.5 also dark fringe. Okay. Right, so that those that we have discussed is for the coherent sources in phase. Okay, next. Oh, sorry, we have a table over here. So you can see here the central bright is when the delta L is equals to 0. Okay, and the first bright is when delta L is equals to lambda, and the second bright is 2 lambda. Then for the first dark, okay, we say that to get a dark region, delta L should be half lambda. So half lambda, 3 over 2 lambda, 5 over 2 lambda. So that will produce a dark region. Okay, so this is for in phase when they start with the same cycle. Okay, so next is the path difference for constructive interference for anti-phase. Just now we are looking at in terms of in phase. So this one anti-phase. Oops. Okay, so for anti-phase coherent sources, you can see the S1 starts with the positive cycle, S2 starts with the negative cycle. So this one showing that they are anti-phase. Okay, but to determine the types of interference, we need to look at how they meet at a point. Okay, so here they are meeting at the same point, and starting from this point, they will move constructively as one wave. Okay, so let's try to count the difference in lambda. Okay, my cursor gone. Wait. Okay, here. So this one is 1 lambda, 2, 3, 4, 5.5 lambda. Okay, for S2, 1, 2, 3, 4, 5, 6. So we have 6 lambda minus 5.5 lambda. So the difference is half lambda. Okay, so in the case of anti-phase coherent sources, to get constructive, they need to have delta L, a difference of half lambda. Okay, so it can be 1.5, 3.5, and 2.5. Okay, sorry, I think this one it should be first bright fringe, second bright fringe, and third bright fringe. Okay, because we are talking about constructive. Okay, so this one is wrong over here. Okay, then destructive interference for anti-phase. Okay, so they are anti-phase when we can see that the cycles are the opposites, and then when they meet at a point, okay, for destructive, they should cancel out each other. Okay, so in terms of the wavelength, so this one is 1, 2, 3, 4, 5, 5.5. So this one is also 1, 2, 3, 4, 5.5. Okay, so the difference is 0. Okay, so for destructive interference, for anti-phase, they should have delta L equals to m lambda. So let's see if we got the, so this one is the opposites of, this one is for the previous slide. Okay, so you need to understand destructive, we always get dark. So this one is wrong over here, sorry for that. Okay, so interference pattern for two coherent sources in anti-phase. So for anti-phase, the central starts with dark. Okay, so we say that we can get a destructive interference when the difference is equals to m lambda. So 0 lambda, 1 lambda, 2 lambda. Okay, for bright, a difference of m plus half lambda. So this one is 1 plus half lambda, 2 plus half lambda. We will get dark region. Okay, sorry, bright region. It's quite confusing, right? Okay, so this is summary of what we have discussed earlier. Okay, so for in phase, for constructive interference, delta L equals to m lambda. For destructive, m plus half lambda. Okay, but for anti-phase, it's the opposite. Okay, so this one is the same as this one. This one over here, can you see the slide? Okay, this one is the same as this one. Okay, so it's easier for you if you just understand and maybe memorize for in-phase interference. Okay, right, then we go to lesson check. Okay, we're almost done the lecture. Okay, the first question for 7.2. Right, so which of the following statement is true concerning monochromatic light waves that are coherent? So the answer is B. They have a constant phase difference. So this one, I mentioned that they maintain the same phase difference from starting till the end. Okay, so some books might also use same phase difference. Same is not the right answer. It should be constant, meaning that the difference is constant. Okay, you cannot put same. Okay, because the two sources might start with a different phase angle. Right, then we go to lesson check 5. Okay, so interference is observed only when the phase difference between the two waves is 0. So the answer is false, because for